You hear from Professor Sijue from University of Michigan. Professor Wu has made fundamental contribution to a field of mathematical fluid dynamics, especially mathematical theory of water waves. And Professor Wu is also the awardee of the Frontiers of Science Award this year. The title of the talk is on the motion of water waves with angled crests. Let's welcome.
Okay, so thank you for the introduction, and I would like to thank organizers for the invitation. So I'm going to talk about water waves, in particular with angled crest. I'm trying to give my explanation of this kind of thing, okay? But of course, you can always have your own explanations. So anyway, so as a mathematician, we simplify the matter. We assume the density of the air is 0. So that means we will neglect the wind, okay? And the gravity is 0 minus g. And the density of the fluid is 1. And we will also assume that it's incompressible and irrotational, okay? So the equation is the following, okay? So the air density is 0, and the fluid is also irrotational, incompressible, but it's also inviscid. So basically, we are looking at a very large scale, like in the ocean, okay? And we also assume the surface tension 0. So that means we are not going to care about small scale, like motion, like ripple, okay? So we just assume surface tension 0. And now the fluid domain will depend on time, right? So if you imagine what's happening in the ocean, then also sigma t indicate the interface at time t. So the fluid motion is described by the Euler equation. So the v is velocity, the left-hand side is acceleration, and the density is 1. So by Newton's law, density times acceleration equal to the force. So right-hand side is gravity, and p is pressure. So p is described internal force, okay? And this is incompressible, irrotational, and because the surface tension 0, the air density is 1, so there's nothing happens on the interface. So the pressure is 0 on the interface. Okay. So for this problem, there's an important sign condition. It's called the Taylor sign condition. Basically, so this n is the unit outward normal to the fluid domain. Okay. So in other words, the pressure is required to be increasing in the normal, inward normal direction. Because if the sign is opposite, so there's a force rip open the fluid, and of course the bubble will form and it becomes ill-posed or instability, okay, will happen. So this condition was proposed by G.I. Taylor, okay, and it is well known that when the Taylor sign condition fails, the water wave equation is ill-posed. This is a result of ebbing, for example, and I'm going to get this a little later and to see why the sign is so important, okay? And of course, between 0 and a lower positive bound, so we call this, with a positive lower bound, a strong Taylor sign condition, okay? Okay, so there are many, by now there are many studies on the water wave problem, okay? So here this is the more recent results, just local well-posedness in Sobolev space. So the first work was done by Nalimov in 1974 for small data, okay? So if the data is small, and this is infinite depths and 2 space dimensional, and Yoshihara is also small data, but there's a fluid bottom that does not interact with the interface, okay? So if there's no interaction of the interface with the bottom, and both in 2D and the same with water grade. So in 2D, there's a local, for small data, you can solve the equation for a short period of time, okay? So in this work, we showed actually the smallness can be completely removed. So in other words, the interface even can overturn, okay? So it doesn't really matter, just any Sobolev data, and you can solve for some finite time, okay? So the crucial to this result is the so-called Taylor sign condition. So we actually were able to show that the strong Taylor sign condition always holds, okay? So in other words, there's always a positive lower bound as long as the interface is smooth enough, like C1 gamma. Gamma is positive, any positive. And there are many development in the local well posedness. So now it's like you can add a surface tension. So surface tension is smoothing term, right? And it doesn't make matter worse. And you can also have a non-zero vorticity, and the vorticity is a lower order term, and that's also okay. So then, we can then, but in all these situations, the Taylor-Sum condition doesn't hold automatically. And then you just assume that the Taylor-Sum condition, strong Taylor-Sum condition holds, and then you can solve it for some finite time. Okay. Okay, so by now there's also a lot of work on the global behavior for small, smooth, and the localized data. So this means that there's really not much going on at spatial infinity. Okay. So, and the main idea is that, so basically, so in these two work, we show that for 2D, you can solve for almost global in time. So in other words, if data is of size epsilon, you can solve for time e to the 1 over epsilon. And then global means that you can, for data of size epsilon small enough, then you can solve for all time. Okay. And Germain, Moody, Chatab also proved global well posedness using a different method, but also they showed there's a scattering. Okay. And Ionescu, Pusateri, Al-Azad, the law independently proved actually for two-dimensional case, you can solve for data small enough for global in time. So the new idea they introduced there is they showed modified scattering. Okay. So there's modified scattering, then you can solve for all time. Okay. And this is another proof. Okay, same result. So the main idea of all this work is that for the water wave equation, after a suitable change of coordinates, a variable and the coordinates, actually the equation will have no quadratic nonlinear term. Okay, so in other words, it's a linear plus equal to something cubic, and we're dealing with something small, right? So if it's small, so it's really a much smaller perturbation of the linear equation. So now, together with the dispersive property, so it's just like if the data decays fast enough at spatial infinity, so you also use vector field method, you can also have a decay of the linear solution in time. Okay, so combine these two. So crucial is localized data, right? So there's a dispersive property, and you can solve for almost global or global. Okay, but if you don't assume that the data is localized, say for example periodic data, and purely so if you have a cubic term, so you should be able to solve time for time e to the epsilon to the minus 2. Okay. So in other words, if you can remove the quadratic nonlinearity, I mean, you just perform the energy method, you can see that this is what you are expected to do. Okay, so the natural thing to think is that, well, what if after some, maybe the equation, you can also do some magic and remove the cubic nonlinearity, right? And then you are supposed to solve for e to the minus 3, okay? So for this matter, in fact, there are a lot of work, okay? So I'm mentioning here. So this is a formal calculation by Dyachenko, Zaharov. They show that by formal calculation, there's no non-trivial full-wave resonances. So in other words, there's a Birkhoff normal form change, and after that, the cubic nonlinearity is still there, but it's an integrable equation. So if you remove all the quartic and the higher order terms, and you get the integrable system. Okay. So this is the first work to make the idea of Dyachenko, Zaharov rigorous. Okay. And they show that for small, smooth periodic data, for data of size epsilon, you can solve for epsilon minus 3. And here we give a different proof, but allowing large, so the data is actually works for a larger class of data, for example, with large slope, and it can be both periodic and non-periodic. And for of size epsilon, you can solve for epsilon minus 3. Okay. So for this, in this work, Ionescu, Pusateri, and they also studied this same question and they can solve for epsilon minus 3 as well. But with incorporating with data which is localized, they can push the existence a little further. Okay, epsilon minus. I don't know. Okay, This will tell you what the result is. So if so essentially all these results say that in some sense the cubic nonlinearity can also be removed, okay, but not completely. In fact, because there's still trivial four-way resonances, so there's some integrable term there. Okay, so there's also a lot of results on local, positiveness in low regularity Sobolev spaces. And essentially it's done by the group of Al-Azhar, Burke, Zuidi, and also later by Hunter, Ephraim Tatalu. So in all this work, they assume that, so the interface is required to be regularity is C3 half plus epsilon, or C3 half minus epsilon, okay? So, but for this type of interface, you won't see angle crest, right? Because it's C1 plus 1/2, okay? So okay, so, and in all this work, as we mentioned earlier, the strong Taylor-Sine condition holds, right? Because as long as the interface is C1 gamma positive, the strong Taylor-Sine condition holds, okay? So with a lower bound, positive lower. Okay, so now this is what we want to see, right? So we often see things like this in the ocean. So the question is, how do we understand these kinks there, right? The angled crest, okay? So certainly this is not C1 alpha, right? Because it's not even C1, okay? So the question is, so does water wave equation admit such solutions, right? And the question, once the wave with angled crest form, does it persist? Okay. So of course, I mean, it's well known that if the wave forms, so for example, something happens in Japan, and the wave can move all the way to California, right? So it can just persist. It can just continue. And so whether some storm in California, in Japan will eventually move to California and keep the angled crest form. Okay. So essential question is a water wave equation well posed in any class that will include non-C1 interface with angled crest? Okay, so the first thing we want to understand is what are some typical type of singular interfaces, okay? So again, we are going to think about self-similar solution, right? Because self-similar, I mean, the importance Tarek has just explained, right? And we see self-similarities. In fact, I mean, in physical motion, if you see the phenomena for a long time, it does assume some kind of self-similarity. Okay? So you want to understand whether there are self-similar solutions of the 2D water waves. And we think that, well, with the wave like this, it should be just where the convection is in dominance. Okay. So in other words, the spatial variable should scale like time variable. So this is a hyperbolic scaling. So the velocity is in dominance. But in fact, in the water wave equation, if there's a gravity, the gravity is in dominance, you cannot use the scaling. So we have to remove the gravity, okay? If the surface tension is there, this scaling also fails. So we have to neglect both gravity and the surface tension. So this is really a very idealized equation. And we just say that, what will we get? Okay, so it's like, but we have just seen that strong Taylor-Sine condition is very important, right? Because otherwise the bubble form, the problem is ill-posed, and it's unstable, and you're not going to see anything. Okay, so we assume the Taylor-Sine condition holds for the solution we find. So neglect gravity, surface tension, and you plug in this ansatz. Okay, so you plug in this ansatz. It's very simple. You just plug into the Euler equation with a free boundary. Okay. Once you plug in, you realize you don't really have a lot of choice. Once you get to this equation, there's really no deep analysis. You just plug in and you find you can only have wave, if it exists, of this form. So you can just say like concave up, right? So, but you can just keep going concave up, concave up. But we never see waves like concave up and then go up like this, right? It will always go down, okay? So now we impose a term of the angle, okay? So concave up, and then it turns by a certain angle, and then concave up again. So where does this concavity come from? This is really because of the Taylor-Sine condition. Okay, so positivity, second derivative positive, and Taylor-Sine condition somehow is related to the second derivative of the interface. Okay, so you have the concavity is due to the Taylor-Sine condition hold, and the interior angle has to be no more than 90 degrees. Okay, so where does this come from? This is like if you really allow over 90 degrees, then you will have this wave roll up infinitely times, and which is also non-physical. We have never seen wave which roll up infinitely many times. Okay, so the only way we can find is this is less than 90 degrees, and this is concave up and concave up. Okay, okay, so this is the reason. Okay, so the outer angle is greater than pi over 2, and it's due to Taylor instability. And we can actually such wave exist. Okay, so with symmetry. Okay, so here are just some photograph I took just to convince you that they are wave like that. Okay, so this is like, since I need to move today fast. Okay, so I'll just show one of this is in San Diego. This is one of the, I blow up the photo I took, and you can see the wave really concave up on both sides, right? And there's a kink in the middle. Okay, so it's like, you know, if you just you're a surfer, you say, well, I asked of surf because I don't surf. I didn't believe myself at the beginning, right? How come the wave concave up on both sides? But there's a surfer says, of course they concave up on both sides. Okay. So which is say that, okay, well, it's not bad. And this is from internet. You have waves concave up both sides, and then there's a kink. Okay. And of course, less than 90 degrees. And this is on the, you know, this is a photo I took in Paris, just over one of the bridges, right? And you can see the wave behind the boat. It's also like that. Okay. So this is, okay, and then, of course, I mean, if you look carefully, it looks like this one, of course, have wind over it, right? So the concavity may not peak, okay? Okay, so this is one of the early results. Now, of course, the next questions, do we have well-posedness of the water wave equation in any class that includes non-C1 interfaces? So here I have to go a little slower. So how do we solve the equation? Okay, so here I'm also trying to explain where the Taylor-Sine condition comes in, right? Why it's so important. So the usual approach, because it's divergence 0, curl equal to 0, so this is a potential flow. So the velocity field satisfies the Laplace equation, right? So we only need, so it's Laplace V equal to 0. So we only need to know the velocity field on the interface and then recover it inside Breuil domain. So this is, so we write down the interface equation. So because the difficulty with the water wave, it's a moving domain, right? We don't know how to solve. We hope to fix the domain, okay? So in fact, we are just going to solve it on the interface, because once we know the information on the interface, we can solve it inside. So we identify, so this is just in 2 dimensions, okay? So we identify xy with x plus iy. We use complex variable, okay? So the interface, we write like z equal to z alpha t. Alpha is a Lagrangian coordinate. Then I take, this little t means, zt means velocity, taking derivative to t. If I take 2 derivatives to t, I get acceleration, okay? So basically, I try to write down the Euler equation on the interface, right? So this, I already know the acceleration is ztt, okay? The gravity used complex variable is minus gi. So in fact, later on, I'm going to take this little g as 1, okay? So then the gradient p, because the pressure is 0 on the interface, so the gradient p points in the normal direction, okay? Normal to the interface, and you decompose according to the normal and the tangential direction, so only the normal direction survive, right? So negative dpdn times n is normal. This n, so if interface is z, taking derivative to alpha, you get tangential vector, right? You multiply r, you just turn the tangential vector 90 degrees to normal, right? So I z alpha is a normal vector, order normal, and divide by its length, so it's a unit normal, so you can write like this. But using this equation, you can figure out this little a is just negative dpdn over 1 over z alpha, okay? So this is all, these are just notation. So ZT bar is a boundary value. So we know that divergence V equals 0, curl equals 0, equivalent to V bar is a holomorphic function. So these two equations is just Cauchy-Riemann equation. So you can write this as, so this is a boundary value of holomorphic functions. So this means it satisfies the Cauchy integral formula. Okay. So you write down the Cauchy integral formula. So this is, and you can see that this Hilbert transform is exactly twice of the Cauchy integral, right? Okay. So this is because if you take the limit of the Cauchy integral, you will get like 1/2 identity plus 1/2 of the Hilbert transform. So I just reduce it, so 1/2, and then this left-hand side, it has the whole thing. So divergence curl equals 0 means that ZT bar should satisfy this equation. Okay, so this is, H is a Hilbert transform. This should have a principal value here. Okay, so and the first equation is the Euler equation. So acceleration, negative of the gravity, and this is negative gradient P. Okay, and this is a Cauchy, this is divergence curl equals 0 equivalent to this. But this one is nice to write down, but difficult to solve, right? Because unknown interface is in the bottom as well. And this is very nonlinear. So we will use the Riemann mapping just to flatten out the whole thing, okay? So the Riemann mapping is a mapping taking the lower half plane to the fluid domain, okay? So of course we know that it also takes interface to the interface, right? So this is P minus, and this is your water wave, omega t. So this, say, alpha prime is the variable here, and your boundary is Z prime equal to Z alpha t, psi alpha prime. Okay. This alpha prime is on the line. Okay. So now you can also write down the interface using the Riemann mapping variable, right? Like this. But between the Riemann mapping variable and the Lagrangian coordinate, there's a change of variable, right? So remember this capital Z alpha t, Z alpha prime t should also equal to this in Lagrangian coordinate. So there's a change of variable here. We write it H alpha t. Okay, so this is a change of coordinate here. We use little h to indicate this, and these are just notation. Okay, so between the change of coordinates, capital ZT, this is just notation. This is the velocity in terms of the Riemann mapping variable. So there's a velocity evaluate on the interface, right? And there's a change of variable. So capital DT is DT plus B d alpha. Okay, so this B is just the, I mean, use the chain rule. You will have something like this come out, okay? And then these are just notation, okay? These are just notation. Okay, so we can equivalently write down the water wave equation in terms of the Riemann mapping variable. So again, the first equation is Euler equation. Acceleration, the gravity, and this is negative gradient P, okay? Just up the change of variable. So this A is real value corresponding to the little a, okay? And the good thing about this is that, you know, velocity is holomorphic, V bar holomorphic, composed with Riemann mapping, it's still holomorphic. But this is a holomorphic function in the low half plane, right? So in the low half plane, it's much easier to write down the Hilbert transform. It's just this, okay? So this equation is much simplified, okay? But the pay is that now there's a change of variable here. So we have to figure out everything in between. So this B, for example, it's taking derivative to T itself, you don't get material derivative, and there's a shift here. So you have to compute B. And for this, we already have done, and this A, just a change of notation. You can trace back notation, it's just negative dpdn times 1 over the length of a capital Z alpha. So this capital Z, the capital Z is the Riemann mapping variable boundary. Okay, so this has been done a long time ago, and this is a precise formula. In fact, the reason we compute this formula is we want to figure out what is negative dpdn. Okay, so the formula is simple. It's this one. So this G is gravity. You can think it's 1. Okay, it's 1 plus this something positive, right? So this means A1 is always positive, greater than 1. Okay, and remember negative dpdn is this guy. So this means negative dpdn is always greater than or equal to 0, right? But in fact, A1 is greater than or equal to G, which is positive. So if 1 over Z alpha is never 0, like it's C1 gamma, 1 over Z alpha is bounded above and below, so it has a positive lower bound. So this is how we prove that the Taylor-Sum condition always holds. Okay, so now, and also we have learned in these early works that by taking one more derivative to time, you exactly get a quasi-linear equation. So how do we see this? So this is really, remember the Euler equation is ZTT plus I, ZTT plus I equal to IA Z alpha, right? But so if I put a bar on both sides, I get negative IA Z alpha, okay? So if you take one derivative bar, okay? So if you take one derivative to time, you find that, half of the equation, I have moved, the right-hand side has two terms, right? One term, I keep it on the right. The other term, I move to the left. Because these two terms are higher order term, this is lower order term. So why is this? A simple explanation is ZT bar is holomorphic, right? Boundary value holomorphic. So taking any derivative, you still get something holomorphic, almost holomorphic, okay? Close to being holomorphic. So this is like also taking spatial derivative, IA, the stretch spatial derivative. So this left-hand side is almost holomorphic, but the right-hand side, if you ignore the bar, it points in the normal direction, right? So anything, if you have learned a basic complex analysis, we know that if the tangential direction is 0, the normal direction is also 0, if it's holomorphic, right? For holomorphic function, tangential direction is 0, normal is 0. But since the left-hand side is not exactly holomorphic, so there are some terms and which is a lower order term. Okay, so these can all be computed. And this is a constraint equation, divergence curl equals 0. And we can write like this. So this has all been computed also in the early paper we had. So this is a quasi-linear equation, and this is the material derivative. It's like writing the same equation in the Riemann mapping equation, coordinates, right? Because in Riemann mapping, everything is so much easier to compute. So this is two material derivative to velocity, and this is like IA ZT alpha. And the right-hand side, we can compute it just to be this, okay? And the reason this is a lower order term is we know the commutator gives you gain of derivatives, right? So this is a lower order term. The left-hand side has two derivatives of ZT, spatial derivative, and even, the right-hand side looks like it's much better, okay? And the same here. Okay, so this is a quasi-linear equation, and everything is figured out here. So now I think it's just a remark, okay? So what is I d alpha ZT, right? So if the ZT bar is holomorphic, it satisfies it equal to the Hilbert transform of itself. So I d alpha H together is just absolute value of d alpha. So this means that this is a positive operator, right? It's a Differential normal operator, which is positive. So the positive, it's just like we are really looking at something like dt squared plus square root of minus Laplacian, right? And this, okay, roughly speaking, okay. So this is a wave type of equation, so it's hyperbolic. So this is why it's locally well posed, okay. So an active dpdn is this guy, and the quasi-linear equation this, okay. So this is just a lower order term, okay. So the conclusion is, in this smooth region, because this coefficient has a positive lower bound, the equation is hot type, okay? So let's see, and we have, this is how we did it, the local well posts, okay? And, this is the equation, because 1 over z alpha has a positive lower bound, so this coefficient is strictly positive, and multiply a positive operator. So I should really put A1 over Z alpha square here. Okay. So everything's fine here. Okay. 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 So now we want to see angle crest. Okay, so what is really the issue with if we want to deal with singularity? Because when we deal with singularity, 1 over Z alpha has to be 0, right? Because why? Because 1 over Z alpha. So if you have a Riemann mapping to the lower half plane to something like this, right? So this is the psi will satisfy psi Z T is roughly like Z to some power mu. Okay, some power, right? And this angle is pi, this is 0, and this is mu pi. Okay. So this means that if you go like this, mu is less than 1. Okay. So if you take one derivative, you will get Z to the mu minus 1. So this means that the derivative, if mu is less than 1, 1 over Z alpha is infinity, right? If you plug in 0, it's infinity at the origin. Psi Z 0, T equal to infinity. So 1 of this is 0. Okay. So this angle, of course, you can say, well, we can also think about this angle bigger than pi, right? But we don't normally see wave like this. Okay, if the angle is less than pi. So why the interior angle we care about is less than or equal to pi? Because we have this equation, right? So remember this equation, where does this come from? This is really the Euler equation, right? Acceleration plus gravity equals to IA Z alpha, right? So this is like here I just move A1 to the right-hand side. So now I have replaced little g by 1. Okay, so so we normally see waves with finite acceleration, right? So that means the right-hand side has to be finite. So this means 1 over Z alpha cannot be infinity, right? If it cannot be infinity, so the angle has to be less than 1, less than pi. So less than or equal to pi, okay? Okay, so now why should we expect to solve the equation even if 1 over Z alpha is 0, okay? So if you just look at the evolution, so this water wave equation, basically, I mean, to understand the water wave, we only need to understand two quantities, velocity and the shape of the domain, right? The velocity zt, the shape of the domain is determined by its Riemann mapping, okay? So these are two unknowns involved, and you look at the evolution of the 1 over Z alpha, you get something like this. I mean, this is just computation we did some time ago, okay? So I just quickly write down the formula. It's easy to compute. So you look at the evolution of a 1 over ZT bar, you get this. A1 is this. You see the right-hand side makes perfect sense. Is a function of ZT and the 1 over Z alpha anyway. You never see Z alpha itself, okay? So it's fine even if 1 over Z alpha is 0, okay? The trouble is just that if 1 over Z alpha is 0, this coefficient becomes 0, okay? That's the only problem, okay? So that means it's not so hyperbolic anymore, right? So if so the difficulty is, if you look at the quasi-linear equation, this coefficient will vanish where there's an angle crest, okay? So this is 0, okay? Okay, so now here I'm just going to state the theorem we proved. So the theorem is basically, I think that the crucial is we realized this is the energy, okay? So if you try to understand how do we construct, so crucial is we would like this to be in L2. After that, so this is d alpha square, capital D alpha is like this. So d alpha square is really like, okay? So I put the quasi-linear equation here, okay? dt square plus I A1 Z alpha square d alpha ZT bar equal to lower order. Okay? So now if you have ZT alpha in L2, right? But the next time when you want to take derivative, you think this whole thing is a full derivative. So remember, A1 is greater than or equal to 1. But being this guy in L2 also means it's less than a constant, okay? So in other words, the next derivative you want to take is 1 over z alpha squared d alpha. Alpha. This is in L2. This is equivalent to the second term. This is this one. And of course, 1 over z alpha is really acceleration, right? Remember, 1 over z alpha is 1 over I, or 1 over I, ct bar minus I over A1. Okay, so remember, A1 has both upper and lower bound. So 1 over z alpha is equivalent to ztt bar. Okay, so acceleration, taking spatial d alpha is in L2. And so it basically is really this one in L2, but this one in L2 is equivalent to dt squared of ct alpha in L2, right? Because, if you look at this equation, one derivative like this is equivalent to this. Okay, so you can, equivalently, you can just keep taking material derivative of this guy. Okay, so take material, so this is essentially take one material derivative of this one, and you keep taking two more material derivative of this one, you get this one. So this is how it works. Okay, so this is a term when you write down the energy estimate, there's a second term coming from here. So these are these extra terms. So the result is we first, with my former student, Rafe Kinsey, we show that if this energy is finite, there's a time, finite time, and the energy stay finite for some time, okay? Okay, and then in this work, we have proved that, in fact, the water wave equation is well posed, locally well posed in this energy class, okay? Okay, so what is, these are just some remarks, okay? So if you look at carefully, this energy class really just, it looks like everything's fine, except that when you take derivative, you would take one weighted derivative, right? So it does allow 1 over z alpha to be 0, because if 1 over z alpha is 0, it's completely fine. It can still be finite. But of course, if 1 over z alpha is not 0, it's also fine, right? So it does include all the Sobolev data like usual. Okay, so all we need is these two is in Sobolev. Okay, so if all this is in L2. So it allows the angle crest, okay? And then, so one remark, the self-similar solution we calculated has finite energy because the interior angle is less than pi over 2. So this angle is less than pi over 2 for the energy finite, the self-similar solution. Therefore, it has finite energy. And in general, surface that have angle interior crest no more than pi over 2 has finite energy. But the Stokes wave of maximum phi height is like, more than pi over 2, right? So what's that angle? 60 degrees? No, what? 2 over 3 pi, okay. What's 2 over 3? Okay, anyway. So that has infinite energy. So this is a disappointment, right? So why less than pi over 2, okay? So even though we seem to be, should be happy that, we construct a self-similar solution, it requires pi over 2, less than pi over 2, and we have this nice energy class. In particular, when we do the energy estimate, we find, everything worked out so well. So we were very happy, okay? But the main idea of proof is that, you really treat this derivative like this derivative, okay? So the main idea, we find the regime that allows C1, non-C1 interfaces, which we also allow C1, C infinity, just regular phase interfaces as well, right? Because the definitely still work, okay? And the equation behave like this. So instead of thinking this like something becomes 0 times something non-zero, you just think this whole thing is a derivative, a spatial derivative, okay? So here's a remark. So Siddhant Agrawal, so my former student, have shown that, in fact, the solution in this class can also be obtained as a zero surface tension limit of capillary gravity waves, okay? Now, there's an important observation first done by Rafe Kinsey, okay? So in fact, he noticed that the energy class we constructed does not allow change of angle, okay? So why is this, okay? And this is observation was proved rigorously by Siddhant. Okay, so why is this? So let's go back to the energy class. It's very simple to see. Okay. Is there an eraser somewhere? Oh, okay. So it's really just because of the energy class we have constructed. So, okay. And you can see that, why this? So remember, this is P2, this is the angle, right? Mu pi. And then this means that this is 0, 0. Okay, so this means pi psi 0, t is roughly like c to the mu. Okay, so now, so 1 over the, so psi z, so in other words, it's z, capital Z, alpha prime t is roughly like alpha prime mu minus. Okay, so if you just look at zt alpha, okay, zt alpha in L2 means that, so we can write this as z alpha times 1 over z alpha. Oh, can I erase this? Okay, so it's like zt alpha divided by z alpha. Okay, now z alpha in L2 means mu has to be bigger than pi over 2, right? Okay, this is not in L2 if mu is less than 1. Okay, because, it's very simple to compute. Okay, so this, it's like 2 mu minus 1 needs to be minus 2 to be bigger than minus 1. Okay, so mu should be bigger than 1/2. Okay, but this contradicts with other one, right? So d alpha, 1 over z alpha in L2 means that mu has to be less than 1/2. Okay, but this requirement means that this is in L2 means this guy cannot be in L2. So the only way this whole thing is in L2 is this is 0, right? So the only thing, this implies that zt alpha divided by z alpha, and then you calculate. So if I just go back to the Eulerian coordinate, it becomes zt alpha divided by z alpha, and this is like dt natural log of z alpha, and this has to be 0 at 0, right? So this 0 equals to this 0 and has to be 0. And the only way to do that, right? Because this power itself is not in L2, but you have to multiply by 0, it's fine. So it requires this in L2, but what does this in L2 means? Natural log of z alpha equals to the length of z alpha plus I argument of z alpha. Argument means the angle, right? So the angle cannot change, okay? Because the derivative 0 means the angle doesn't change, okay? So this is really why the angle doesn't change. It's really because of the energy class we're dealing with is that, okay? So but essentially, at the crest point, what I'm computing here is, this is, if you sit down and compute, this is really the spatial derivative in the z variable. This has to be 0 at the crest. This has to be 0. So then this means that, well, does the water wave really admit angle crest waves of changing crest angle? Okay. So in order to do this, you need this to be non-zero, right? Otherwise, it will not change. If this is 0, means the angle doesn't change. If the angle changes, this guy cannot be 0. Okay. Okay, so just a remark of recent work. So Siddhant Agrawal construct a class of energy. So this energy is almost equivalent to the energy we were using. Okay, so similar energy but rearranged, and he can show that this energy, in fact, has with a contradictory argument. He showed that there are solution which has finite energy and becomes infinity at some time. Okay, so there's a norm inflation for the class of energy. So, but his energy is more refined than what I have just shown you. Okay, but in the essential class. So in other words, his energy also doesn't allow the change of angle. Okay, the angle has to be less than pi over 2. So in this work, Cordova and Cecil Grubik show that the water wave equation, in fact, admits solution in class where the angle crest and interface has a changing acute angle. But in this work, they require that the interior angle is still less than pi over 2, okay? So a natural question is, how about angle bigger than pi over 2? I mean, it's really, why is there such a less than pi over 2 thing? Okay, so let's just take a closer look at their work. So here, I think this is basically my interpretation of their work, okay? So it turns out, I mean, of course, they try to find just perturbation of this type, okay? So their velocity is like, it's a linear term like this. Basic requirement is B1 is not zero, right? Because this means the derivative is not zero, but plus some further perturbation, okay? So here we just look at, stop here, okay? It turns out that this is a special solution of the water wave equation. So what is a special solution? So if you look at this, this means the water region is has a fixed arm. Okay, it has two fixed arms. It's like that. This is completely straight line. Okay, so it's like it can just go up like this. Okay, straight line moving up like this. Okay, you see, crucial is this mu change with respect to time. This change with time, and this is artificial. You can also allow this point change. But that's not that important. So what's important is these two change with respect to time. The velocity is linear function, okay? And the pressure, you just take this way, okay? So this is B1, same this is quadratic, and this is a real part of this thing, and you can compute with this formula. In fact, V1, P1 solve the water wave equation on the fluid domain, okay? If and only if these parameters involved satisfy this linear ODE, okay? And by observation of Eric Wackel, and he noticed that this ODE in fact has a solution which doesn't exist for all time, okay? That blows up at finite. Okay, so in other words, the water wave equation has this special solution which becomes, you know, the quantity B0, or I don't remember, one of the quantity becomes infinity at some finite time, okay? Now, if you look at this, right, so this is equation, of course, certainly satisfied also if the angle doesn't change. If the angle doesn't change means that B1 is zero. So you can see if B1 is zero initially, it stays zero all time, right, because of this equation, okay? So this is the, okay? Okay, so now we can use this to explain why the angle has to be less than pi over 2. Okay, so the basic argument is that turn around this special singular solution. Okay, see this special solution, and you find a solution that was changing angle. So you compute for this special solution, find negative dpdn equal to this guy. And if the interior angle is bigger than pi over 2, then negative dpdn is less than 0. The Taylor-Sum condition doesn't hold. So the special solution is not physical. So certainly you don't want to perturb around a non-physical solution, right? So everything. Okay, that's one reason the angle cannot be greater than pi over 2. Another reason is also you want this singular solution to be dominant, right? You want this special solution to be dominant. The only way is, so you compute A1, you notice this is what happens, right? Remember A1 equals to 1 plus something. So it should be like this. Now, in order for this to be dominant, mu has to be less than pi over 2, right? Less than 1/2. Because if it's bigger than 1/2, this is close to 0 at this point, then it's not dominant anymore. Okay, so that's another reason that you don't deal with greater than pi over 2. Okay. Okay, so definitely it doesn't mean that the water wave equation doesn't allow interior angle bigger than pi over 2. It just means that it requires new ID. So I think I have probably used up all night. Yeah.
We have time for one question.
Yeah. conservation? That's a good question. I think that in both cases, so no, there's no conservation, but no, there's no conservation. But in my case, because the angle doesn't change, so if you have n crest, it remains n crest. But in Cordoba's group's computation, if there's initially one crest, it remains one crest as well, right? Because the argument is perturbing around this one, particularly around this one. But there's no conservation. No, there's the equation, at least not as far as I know. That's right. That's right. Actually, yeah, infinite. My class allows arbitrary many. So essentially, it's really just that's the only requirement. This is finite, and of course, you certainly can allow 1 over the alpha to be 0. Yeah, or not 0 is fine also. So
You have to stop here. If you have more questions, you can approach Professor Wu personally afterwards. Let's stop here and thank our speaker again.